the next speaker of this morning, Andrea Young, is going to tell us about orbital magnets, Pomeranchuk effect, and the entropy of disordered isospins in twisted bilayer graphene. Andrea, I will give you 5-minute warning.
Okay, thanks. Okay, good. So let me tell you what I'm going to tell you. So I think I want to start this talk by talking about what we've learned. It's obviously going to be a selective list about twisted bilayer graphene and related Moire systems since this conference last year, and then sort of tell you about some recent experiments that I think are related to answering some of the questions that I'll pose, spanning the basic topic of orbital ferromagnetism in Moire systems and ultimately how it relates to also to a variety of other phenomena that have been observed. So let me start by sort of giving at least a few reminders of where we were last year and what has happened since. So if you remember last year, we had recently learned about superconductivity in the system. Dima Efetov showed further evidence of superconductivity at a variety of other filling factors besides near nu equals plus and minus 2. And since then, actually, superconductivity has kind of proliferated in twisted bilayer graphene. Most recently, in the last 6 months or so, several reports of superconductivity without the observation of correlated insulators in the immediate proximity. So superconductivity has seemed to have gotten more ubiquitous in this system, and certainly raising more questions, right? If this very first observation from Eun-Ah and Pablo was kind of simple looking, things seem to have gotten more complicated since then. At the same time, there seems to be maybe I would call it in the intervening year, there's been a proliferation of not superconductivity in not twisted bilayer graphene. So a year ago, we had starting, preliminary reports of superconductivity in double bilayers. Shortly thereafter, an ABC on HBN. There have since been other claims in a variety of other systems. But I think more recently, and I'll come back to this at the very end of my talk, there may be at least a growing question of whether any of these systems actually harbor superconductivity. So what looked like a crowd in 2020 turned out not to be, or at least not to be the crowd that we thought it was. That's not the only situation in which that has happened. I'll assume you're all laughing on a Zoom talk. You never get any feedback, so I'll assume that joke really killed. Okay, there was another thing that came up last year and was sort of extensively discussed at this workshop, which I think also I have something relevant to say about today, which is this question of linear T resistivity at, let's say, intermediate temperatures. And there were two really conflicting pictures of this a year ago, and they were both based, I think, I'll argue at the end, based both on a somewhat selective reading of the fact pattern. So Pablo talked about the observation of some linear T resistivity down to pretty low temperatures, sort of sub-Kelvin temperatures in some twisted bilayers at some densities. And Matt, I think, talked about the fact that, in collaboration with Cory and Cory's group, we had observed this linear T that was more or less everywhere. Sometimes it went down to very low temperatures, other times it didn't, but it was more or less everywhere. And so this led to kind of two conflicting pictures. One was to say this is closely related to, let's say, superconductivity or whatever the underlying state around superconductivity is, and the other to say, look, if it's at every density and indeed at a very wide range of twist angles, the mechanism must be rather general. Why not phonons? And Shankar gave a very entertaining talk last year about linear T in general and how this might work out. So that, that was something that I think in the last year we as a community haven't made particular progress on. I'll try to present something about that today. And then the other thing that we just had a hint of a year ago was magnetism. So David Goldhaber-Gordon showed this data on magnetism in twisted bilayer graphene aligned to hexagonal boron nitride. And since then, this has turned out to be a very generic feature of these systems. So observed now, I think, in many of these systems. So we since confirmed that in twisted bilayer graphene. There was an observation of a similar magnetic effect in ABC on hexagonal boron nitride, also in monobilayer graphene. I think there are also indications of it in twisted tungsten selenide. And not only is this magnetism confirmed, but in fact, the sort of speculation at the time was that this was an incipient quantum anomalous Hall effect, and indeed, that is certainly turned out to be the case. So, so the way I'm going to structure my talk is I'm going to talk about some of the kind of unusual phenomenologies of these orbital magnets that have sort of occupied a fair amount of our efforts in the last year, and then I'll try to tie that back to, I think, that the underlying physics of twisted bilayer graphene, and show you some unpublished data about that. So the basic story of orbital magnetism and twisted bilayer graphene is relatively simple. I think Ashvin's already given a beautiful introduction to the basic physics, which is, so in Ashvin's picture, you know, when you don't have a sublattice splitting, then it's natural to think in the basis that he told you about to consider interactions. But once you put on a large sublattice splitting, that can easily become dominant. And we know that when you align monolayer graphene to hexagonal boron nitride, you can open up a band gap in monolayer graphene as big as 30 or 40 millielectron volts. That's very big compared to any bandwidths, and big compared to more or less any other scale in the flat band problem. And so what we find in samples like that is that they look rather different. So this is a sample that's aligned to hexagonal boron nitride. It has a very large energy gap at charge neutrality. And then, you know, most importantly, at 3 electrons per unit cell, there is a quantized anomalous Hall effect. So you're seeing here RXY and RXX being plotted, and there's a quantized RXY and a vanishing RXX. And if you measure magnetic hysteresis, you find that in fact this is quantized down to 0 magnetic field and quantized to a high degree of accuracy. So the understanding of this is relatively simple, at least at the level of hand waving, which is that once you have this gap, you're gapping out the Dirac points in the 2 valleys. And when you gap out a Dirac point, you generally generate Barry curvature. And in fact, you know, a single particle calculation shows you that you will generate churn 1 bands in every for every spin and valley. So if it's spin degenerate, then you'd have churn 2 and -2 in the different valleys for the valence and conduction bands. And then if you ask what's the ground state at nu equals 3, which is just like emptying 1 electron out of the fully filled flat bands, numerical simulations and kind of analogies to quantum Hall ferromagnetism would suggest that, you know, it's not hard to find a state where you simply fill 1 of these churn bands for a single spin and a single valley. But one of the remarkable things about these types of magnets is that the anisotropy that allows you to have a finite temperature phase transition is all coming from the valleys. That in fact, there's very little spin orbit coupling in these systems. So, so this is fundamentally an orbital magnet. As we'll see, that turns out to have some interesting implications for the types of games and one can play and phenomenology one can observe. But at a more prosaic level, something that we noticed right away is that these systems are actually very clean if you compare them to other quantum anomalous Hall systems. So in particular, you can measure the activation gap of electronic transport, so the energy gap of this quantum anomalous Hall state, and find that it's in the range of 30 Kelvin, while the magnetism itself is actually characterized by a sort of a Curie temperature that's a third or a quarter of that. So this is an Arrow plot, and you have a Curie temperature extracted from there of somewhere between 7 and 8 Kelvin, a small fraction of the induced electronic gap, which is kind of remarkable. I mean, I think that's more or less in line with theoretical expectations, although calculating this is not so straightforward, I'm told, and suggests that in fact is not really disorder limited, and that's very different than, say, transition metal doped topological insulator thin films, where you might have Curie temperatures of 20 or 30 Kelvin, but electronic energy gaps of 1 Kelvin. So very much the opposite situation. One of the experiments we've done to try to understand this better is to see if we can understand the role of disorder directly by magnetic imaging. So this is actually a rather challenging experiment because you're sort of naively expect moment densities of 1 Bohr magneton per unit cell of that order, maybe somewhat bigger if since it's an orbital magnet, and that's equivalent to, you know, nanoamp currents that you have to detect. And so if you want to detect that magnetically at, let's say, 100 nanometers separation, you're only talking about nanotesla, you know, 100 nanotesla scale magnetic fields. So okay, so the way we did that is by nanosquid on tip microscopy, which is a technique we learned from Elie Zeldov's group at Weizmann, who have developed this over the last years. And so this is a lovely technique where you can use a very small tip of, you know, where the tips we're going to image with are of order 200 nanometers. That gives you exceptionally good magnetic field sensitivity, about 15 nanotesla per root hertz, and allows you to operate both in finite magnetic fields and in close to zero magnetic fields over a range of cryogenic temperatures. So this is challenging. I'll just make an experimental digression of how we were able to do this. Again, borrowing techniques developed by Ellie's group. Because you need to measure at some finite frequency, we couple the tip here, shown here, to a quartz tuning fork, which allows you to oscillate the tip back and forth at 32 kilohertz. It's just a watch tuning fork. And that allows you to detect response of the squid at that tuning fork frequency that's proportional to the gradient of whatever signal it is that you would be measuring DC. And this is kind of key for us because these signals are very small and these squids are not very good in the DC limit. So you need to have some way to modulate the signal, and it's hard to periodically modulate metastable magnetic structure, which is ultimately what we're trying to do. And this is something that you can calibrate quantitatively. Here are measurements of some thermal gradients measured by tuning fork, and then measured at DC, where you can get a large signal and you can compare, so you can know exactly what constrain the direction and magnitude of this oscillation. So let me just show you what the data looks like. So if you want to look at this orbital magnet, the way we do this is we can measure with respect to different magnetic field preparations, but measure at the same magnetic field of, let's say, 22 millitesla here. And this is what the sample looks like. This is the same sample that shows this beautiful quantization. And we see right away that, you know, it's not perfectly magnetically uniform. If this were a perfectly magnetically uniform sample, you might expect there to be signal along its boundaries, but not in its interior. We see right away that that's not the case. And we can, in fact, from measuring this in for positive and negative field preparation, we can show what the full magnetic structure looks like. So this is actually the tuning fork measurement. So this is, in fact, a derivative with respect to this vector of the static magnetic field in this device. And in black, you see the outline of the device, and the scale bar is about a micron. So there's plenty of submicron structure, about resolution limited for our 200 nanometer tip. Using some sort of standard Fourier domain techniques and integration, we can actually reconstruct the magnetic moment in this device, and we find that it's indeed rather non-uniform. But the thing that I want to draw your attention to for the purpose of this talk is simply that it's rather large. So it's considerably more than 1 Bohr magneton per superlattice unit cell, which we take essentially as sort of direct evidence for the fact that this is indeed a predominantly orbital magnet, simply meaning that the moment per unit cell is mostly coming from orbital magnetism rather than spin magnetism. We don't know at this point whether there's any spin magnetism, whether the spins are actually polarized or they're largely thermally disordered or what, but they're apparently mostly orbital. You can do some cute things that I don't want to spend too much time on.
Andrea?
Yeah.
You have 5 minutes.
Oh my goodness. All right, then I'm going to not spend any time on this and simply skip to something. Then maybe I'll just skip to the unpublished data and talk about that for the last 5 minutes. Time really does fly on Zoom. So I think, you know, what I would have told you about in an hour-long talk apparently is that, in fact, there are many of these orbital magnets and there's some cute things. Actually, that's all already on archive postings. You can find out about it. I want to sort of end the talk by talking about the relationship between these orbital magnets and, I think, some basic features of the phase diagram of twisted bilayer graphene. So in normal twisted bilayer graphene, and by this I mean that it's not aligned to Bn, it doesn't have a gate that's very close to screen interactions in any way. The sort of most typical phase diagram that we see is an insulator at nu, some kind of resistive, maybe an insulator at nu equals -2, strong insulators nu equals +2 and +3. Okay, superconductivity at -2 minus epsilon, right? No orbital churn insulators, right? And no obvious symmetry breaking, for example, at nu equals +and -1. In fact, this is really clear in this particularly clean sample. Here's from 0 to -2, and there's absolutely no sign of a correlated insulator at nu equals -1. Okay, but we know that this can the orbital insulators are not far away. So if, for example, if you put a 4 or 5 Tesla magnetic field, or indeed a 2 Tesla magnetic field at nu equals +1, you have a transition to churn 3 orbital churn insulator, if you want to call it. It takes a magnetic field, but it suggests that the orbital churn insulators are not very far in energy from being the ground state even at 0 field. In fact, recently we've figured out that you can do this also with in-plane magnetic field. So this is as a function of in-plane magnetic field, and you can see that there's this feature that develops close to nu equals -1. There's another peak that develops that was, again, totally absent at 0 in-plane field and low temperatures. And that suggests that, in fact, you can drive some Zeeman effect-driven symmetry breaking. We find this doesn't depend on the direction of the magnetic field in or out of plane very much. So I think this is just a spin-polarized phase that's coupling to the external magnetic field. But the really surprising thing is that this apparently can be driven also by increasing the temperature. So I'm showing you here data as a function of temperature, and you can see that, again, at low temperatures, there's absolutely no sign of any correlated insulator or indeed any symmetry breaking besides the full fourfold degenerate Fermi surface that is kind of similar to what's at charge neutrality. But as you raise the temperature, you develop a new peak around nu equals -1. It's not exactly at nu equals -1, right? So if we zoom in there, the quantity I'd like to analyze is actually the Hall density, but with a linear background subtracted, essentially what you would get if you just had single band physics. And you can see that as a function of temperature, you develop an extra kink in that subtracted Hall density, okay? Which looks like the same thing that happens when you put an in-plane field or indeed an out-of-plane field. Okay, so you can actually compare temperature at which this, which this kink develops, and I'm happy to go through the analysis of how we do that. We just look at where that Hall density changes by maximum, and compare the Zeeman energy required to affect a similar transition. Okay, and the analogy that I want to talk about is that what can temperature be doing to favor order, right? Well, I think what we know from our low temperature, low magnetic field measurements is that the ground state at nu equals -1, where I've been focusing, is not ordered. But as you raise the temperature, what state you're in is determined not by the ground state energy, but by the free energy. And so if you have a very entropic state, then that can compete. In other words, at low temperatures, we'd call it a disordered state, or a state that doesn't have any polarization. It has the entropy of a Fermi liquid. It's very small, but it might be lower ground state energy. But if this ferromagnet has very small spin stiffness, then it can fluctuate, and that gives you a large entropy, right? Something that goes like log n, where n maybe is the number of modes or something like that. And this is kind of the idea of order by disorder, and it is indeed the same thing that happens in helium-3, where for appropriate pressures, you can, in fact, solidify by heating the helium-3, precisely because there's a very small spin stiffness in the solid phase. And there you have a log 2 entropy. This is from Pomeranchuk's original paper, whereas the Fermi liquid has a linear T entropy. And there's a point when the entropy of the solid actually dominates at high temperatures and drives you from a liquid to a solid as a function of increasing temperature. So we think that's what's going on here. We think that has some sort of important implications. Roughly, we can estimate what that difference in entropy is by looking at the critical Zeeman energy required to affect this transition and the critical temperature required to affect it, at which point the change in entropy between the two phases is roughly simply the ratio of those two numbers, right? And as you can see, if I plot them on the same scale, the Zeeman energy and the temperature scale at which this happens are pretty similar, right? So that suggests that there's a change in entropy that's of order unity per unit cell, which is huge. That's a very big change in entropy. So if this structure of how to analyze this is correct, then it's basically saying that in this ferromagnet you have very strong fluctuations. So what does this mean, right? I think that in light of this, I can think about revising my priors on how the physics in the system works. So one thing that I would say is that the linear T is presumably then mostly coming from scattering off of these types of pseudospin waves, right? It explains a couple of things nicely, right? One is it explains the ubiquity. Why is this everywhere? Well, because this sort of ferromagnetic physics is pretty much everywhere in the flat band. There's always a state that breaks some symmetry that is going to be allowed to fluctuate and generate a high entropy, and those fluctuations are going to scatter the electrons. So it kind of neatly ties together, I think, the sort of seeming contradiction here where you have linear T everywhere, but it goes to lower temperatures than phonons really should, right? I mean, since this conference last year, a number of theorists I would trust have sort of looked at the phonon problem, and none of them could really get a Bloch-Grüneisen temperature of, 100 millikelvin. But if you have, soft spin waves and pseudo-spin waves, then it's not very hard to imagine that that happens at very low temperatures. If anything, as Shankar put it recently, the question is, why doesn't it always happen at really low temperatures? But there, I think there's probably just very detailed physics of what ground states are what. I think it also sort of explains maybe why there are these states that look like superconductors to sort of the naive picture, but naive eye, but are not really superconductors, because even if you have ferromagnetic state at low temperatures, apparently it's just going to completely thermally disordered at 5 or 10 Kelvin, and that's going to give you a big change in the resistivity, and that's observed in almost all of these Moire systems, whether they're actually superconducting or not. And indeed, when it's very clearly not superconducting, you certainly see that. We see that in ferromagnetic phases where we're sure it's not a superconductor. So I have a feeling that this is sort of the unifying principle here, is that it's these sort of isospin and fluctuations. What does it mean for superconductivity? Well, so I would say that the idea that the high temperature state is like a parent of the low temperature state actually is not necessarily useful here, because I think in some ways the low temperature states are parents of the high temperature states, because if you have a low spin stiffness, then once you're above 10 Kelvin, everything is going to be dominated by the entropy, right? But I think the important thing for the part of Ashwin's talk that he didn't get to is that if you believe what I'm saying, then the implication would be there's a large entropy and therefore a small pseudospin stiffness. And that's pretty good, right? Because, that's kind of a key feature for this fermion superconductivity, is the idea that there's a low pseudospin stiffness. And I think, this picture is very consistent with a pseudospin stiffness of, 1 MeV or less. That would certainly make it easier for the fermions to happen. I'm going to finish in 30 seconds, Eun-Ah.
No.
Oh.
Actually, you don't have to finish in 30 seconds, first of all, because turned out I miscalculated. So you turned out to have a little more time, thanks to Babek, who correctly pointed out this miscalculation.
Okay, then I'll stop talking quite so fast, but I'm going to rely on all of you to ask questions about all the things that surely were incomprehensible at the speed that I was going.
I'm so sorry, but I just wanted to ask you one clarification request.
Sure.
So you were just talking about the skyrmions and how this would help with the skyrmion-based superconductivity. But in the previous slide, if I heard you correctly, you said a lot of superconductors were misidentified and they were not superconductors.
Correct. Yes. But twisted bilayer graphene is a superconductor.
Ah.
Right. So I think that most of these other systems are not. And if I wanted to sort of go well beyond what any experimental data would really allow me to, I would say that, for the most part, these other systems tend to have pretty clearly spin polarized nu=2 states, right? So I think, you wouldn't, okay, Ashwin will correct me, or his collaborators will correct me, but if I understand that proposal, what you need is, you need a small spin stiffness, but that's a pretty generic feature of all these systems. You also need this KIVC order, and, that's kind of a detailed thing that you need maybe some special features of twisted bilayer graphene specifically, right? And that's not going to be present if you don't have the right symmetries, because you don't have Dirac points and so on, right? Which is generally the case in all these other systems. So I don't know for a fact, but as far as I understand, you wouldn't find this KIVC order in a system that didn't have the Dirac points of twisted bilayer.
Yeah,
Ashwin, is that right?
Yeah, or if you like the C2 symmetry, right?
That's the important thing, and that's broken in all of these other systems, and you get just different ground states.
The HBN or with the double bilayer, yes.
So, that's a very special thing for that particular mechanism, right? Whereas the pseudospin stiffness being small, I think is much more generic, and I think that in fact, it's if you look through all the literature, I think this has sort of been there from the beginning in all of these systems and just not appreciated or not. I don't know. It's there. I mean, it's there in the data from the very first, certainly that we looked at, and I'm sure from MIT and other groups. So, right. So there's another thing.
3 more minutes.
Okay, great.
3
So
more
then
minutes.
there's another thing that I'm basically done. There's another thing I want to just mention, which I think is important, is that, one of the confusions about superconductivity is just when does it happen and when does it not happen, right? I mean, it would have been nice if every sample since the very first report of superconductivity showed the same phase diagram, but they clearly don't, right? I mean, that's definitely not true, right? From this conference last year, it was already getting pretty confusing, and it's only gotten more confusing since. But I think that one of the important things, I'll just go back to kind of try to emphasize this, is that as is evident here, right, this is in-plane field dependence, right? And this is just Rxx, and there's this feature which is starting at, a few Tesla and continuing to develop and moves in density, right? And what we think this feature is based on this subtracted Hall density, right, is that's the phase transition between fourfold symmetry and some kind of spin polarized isospin ferromagnet, okay? But it doesn't have to happen at integer filling. There's nothing really special about integer filling, and I should really acknowledge this paper from Shahal Alani's group was the one that really sort of unclicked this for me to understand just the importance of bandwidth and the density of states in determining where these symmetry breakings really can happen at any density. It's pretty complicated. And so here, for example, if we were just to take a cut along the top, we would never see a correlated insulator at nu equals -1, because at nu equals -1, there's no broken symmetry. But at nu equals 1.3, that's where the symmetry actually breaks, and you go into a state that, all the Landau levels in this region extrapolate to nu equals -1. It is sort of the symmetry breaking associated with nu equals -1, but it doesn't actually happen at nu equals -1. And sorry, I don't have the data to show that, but it's very clear if you put on a little out-of-plane field that all of the quantum oscillations in this triangle actually extrapolate to nu equals -1. This has no out-of-plane field. That would have some out-of-plane field. So I think what that means is that you can certainly have symmetry breaking at arbitrary filling factors that do not actually intersect an integer filling, right? And that's kind of a detailed question. And as a result, it's entirely plausible that the superconductors that we observed and others have observed without any insulators are not superconductors that exist without any symmetry breaking. And in fact, if you look carefully at the Hall effect and the Hall density in all of those measurements that I've been able to see, there's always a little kink that's happening there. And as a result, I think it's possible that that in fact, the superconductivity is tied to some specific symmetry breaking, right? And the most anomalous sample here is actually that sample that Dima showed us a year ago. But if you look at the Landau fan of that sample, it's very different than all the others. So it would not surprise me if for some reason, I don't know, strain, both BNs are aligned, something is slightly different about that sample. In fact, the places where one order or another happens are certainly different than in other samples. So anyway, let me end there and just acknowledge again my group, in particular Charlie, Gregory, and Marek, who worked on the orbital magnets, and you, Saito, who who sent me data, at 2 a.m. this morning on the latest of this Pomeranchuk effect. So and hopefully now there's actually plenty of time for questions. I see a bunch of things in the chat, so let me stop there.
All right. Well, thank you, Andrea. Yes, I can
Thanks.
clap for everybody else, all 300 of us. Okay. So there are a lot of questions. I will start with a question from attendee who cannot speak because of the internet connection. Sarab Srivastav asked about the non-uniform magnetization observations. Can the non-uniform magnetization be due to different local angle, as also discussed in different contexts in Cascade phase transition paper?
Yeah, I think so. I mean, we know in this sample, this is a very good question, right? We know in the sample that the twist angle varies, over macroscopic distances. So, up here, you still have magnetism everywhere, but you don't have quantized anomalous Hall. The angle is slightly different. There's also the alignment and coupling to the hexagonal boron nitride that may be spatially dependent. And right now, we don't have a good way to disentangle those two things. So there's, a couple of, the BN has to be aligned and the two layers are aligned. There can be disorder in both of those. So in short, I don't know what the local moment variation is from, and I don't know what pins the domain walls in particular, right? They certainly are pinned. I think that there are probably lots of orbital ferromagnets that might not be observed because you sort of, the thing people typically look for is hysteresis. But if you had no disorder, you might not have that much hysteresis. So here, maybe we got lucky that we have just enough disorder to give us a nice coercive field, but not so much that it actually screws up the quantization. So yeah, it might be twist angle disorder. It might be other thing. It might be BN to graphene disorder, and we don't currently have a good way to tell.
So I have a question about this picture, this specific slide. I think I've worked hard enough.
Yeah, you deserve it.
All right. So this red and blue color on the left-hand side of your right four panels, if the signs mean something opposite, like somehow in the magnetization, it's not averaging to zero.
So
it went a little too fast.
Yeah, sorry. So what's being measured here is the derivative of the static magnetic field with respect to a vector that points, with respect to that vector.
So I see. It's telling us the sign of the derivative.
Sign of the derivative. So in order to get this, you have to integrate that to generate the static magnetic field, and then do some Fourier transform to get the magnetization. All
right. Thank you. Next question is Raoul Fernandez. You have to unmute yourself, Rafael.
Yeah, thanks. Andrea, very nice talk. I had actually two quick questions. One is just a question about experimental, results. Is it true? So if I understood correctly, there's no ferromagnetism even without a quantized Hall observed if you don't have alignment with the boronitride? And
not that's published.
Okay.
I am told that, with screening you can probably get this nu equals -2 into a ferromagnetic phase.
Okay.
But I mean.
And the second very quick.
And if you look at Dima's previous results, that is very close to zero field.
Okay.
So I think it's probably possible. I don't think there's anything intrinsic about that, but.
Okay. And you talk about magnons, but I was a bit confused. My understanding of this orbital magnetism is that it's just like an icing pointing up or down the plane. Why do you think there would be magnons?
Well,
there?
so I think I think there. All right, I'm being very loose with my terminology, especially when I thought I didn't have that much time. So what I mean is that there's spin, there's valley, there's orbital, and let's refer to all of those as magnons, spin waves, pseudo-spin waves. There's a bunch of degrees of freedom, right? And they are they can have some entropy by flopping around, and they can scatter electrons.
But is it continuous symmetry? That I think is the question. Or is it discrete symmetry of up and down?
I think for the spin part, it would certainly be a continuous symmetry. And probably somebody like Alan would be, I don't know if Alan is here, but he would be the ideal person to ask this, because I know they've looked at this very carefully in terms of actually calculating the spectrum of these neutral excitations. I don't know that for my purposes it matters so much, as long as their stiffness is really small.
All right.
I think we'll have to move on. By the way, Andrea Ellen is here, and he laughed on Zoom for you. But I think there are more questions, so we're going to continue on. Okay. Herb asks a question to Andrea. In quantum anomalous Hall effect, RXY looks beautifully quantized, but not exactly at H. Not exactly. So is it easy to understand why the discrepancy from H over B squared?
I would say that if you look at these plots, your question should be, how is it even possible that this is remotely quantized, rather than why does it differ by a part in 1,000 or something? Actually in the, so there were some contact issues here. If you very carefully, let me find the right plot, but when we're careful to symmetrize with respect to sort of Onsager relations and so on, the quantization here can be very precise, you know, part per thousand. So I don't think that's a problem. When we measure, you know, a little sloppily in transport, as we are wont to do when we're mostly focusing on doing magnetometry measurements, then yeah, there's some deviations, but this is basically contact resistances or other technical stuff that's not very interesting. In the other samples, you know, where it's not really precisely quantized at all, I mean, we know there's twist angle disorder. We know there are various domains. I sort of think we need to make some sort of materials breakthrough a little bit before we can really reliably get, you know, good quantization for these all the time.
Next question. Cory has a question. Cory?
Yeah, so Andrea, I just want to kind of
Yes.
clarify. So the phenomenology that you describe is that basically all systems show some kink in R versus T, and only some systems does that result in superconductivity. But I didn't quite get whether the theory you're promoting would address that all systems actually show a kink in R versus T.
Yeah, I think it does, because I think the picture would be that if it's generally true, let me find it. I'm not sure I have it with me. If it's generally true that you have a bunch of these different neutral modes at over some bandwidth, then at low enough temperatures compared to that bandwidth, those neutral modes will kind of be gone, right? And that'll happen at temperatures of order that bandwidth, and so below that, they won't be relevant. Just like the same way phonons are not relevant below a certain temperature to scattering.
I guess the question, let me just sort of clarify. I guess the question I'm asking is that you're proposing an idea for intrinsic bilayer graphene, kind of what the ground state is in a sense, and what the excited state, or what the phase transition is as a function of temperature. And presumably in the other systems, you're arguing that there is a phase transition, but it's between different ground states.
So in the other systems, I think it's actually just a it's whatever the isospin magnet is, and then it just disorders. In twist, the special thing, right, the thing that was helpful for us is that for a particular range of parameters, let's say nu equals -1 in this particular twisted bilayer graphene sample, you very clearly actually have some kind of phase transition, right, from a disordered state to an ordered state. If you do the same experiment over here, there's no phase transition as a function of temperature. The ferromagnet it just disorders, but it doesn't go from like a disordered phase, an unpolarized phase, I should say, at low temperatures to a fluctuating but polarized phase at high temperatures. And so this is kind of a window because it gives you something kind of qualitative so we could understand it. But actually, the physics I think is very similar everywhere else. It's just that you don't actually necessarily, change from one type of isospin order to another type of isospin order that can fluctuate more and therefore is entropically favored. Did that answer the question? I think it might be easier to talk about it more at length, but
this is the question I was asking. Also, why at filling 1 and not filling 2.5 or something? But that's what you just addressed.
Because at 2.5, the ground state is already the broken symmetry state, whereas at nu equals -1, the ground state is not the broken symmetry state, and that's just details, right? I mean, that's probably different in different samples, and it's different for different systems.
Okay. Next question. I think we have time for maybe 1 or 2 more questions. Yihang Zhang. Can you unmute yourself? Yihang Zhang, can you unmute yourself? Well, maybe it's not working. Then I'll move on to the next question while that gets ironed out. Yonglong Shi is asking, regarding the interpretation of T-linear, are you suggesting symmetry breaking for sample with larger twist angle?
Yeah, that's a great question. I don't know. This is new enough that I haven't been able to think through what this means for like the relatively larger twist angle, and it's a good question, and I don't know the answer to that. I would say that and Leo's experiments on gate screen superconductivity are the 2 things that are still stuck in my mind as like not quite making sense with this picture either. But you will hear more about that, I think, tomorrow. But yeah, I don't know. That's a good question.
Okay, and if there aren't any more questions, I think I haven't missed anyone. I have one last question. The actual experimental evidence of this softness of the pseudospin or isospin is on systems not a twisted bilayer, right? What you showed us was systems on HBN. Am I remembering it correctly? No.
No. So I mean, if I want to summarize, the way I would say that this is the data set in the upper left that is the best evidence for that, right? I mean, if you believe that this peak that's developing at finite temperature is coming from a breaking isospin symmetry, then this is the fact that is telling you that, look, at low temperatures, here's quantum oscillations, no sign of any symmetry breaking between nu equals 0 and nu equals -2. But by 40 Kelvin, you have nu equals something near nu equals -1 that is just on equal footing with whatever's happening near nu equals -2. And so that's the sign that, you have something that is, if entropy is driving that, then that means you have soft modes that are giving you that entropy. And that entropy has to be pretty large, given that this happens at relatively low temperatures compared to, what we estimate that the energy differences between those ground states to be.
Okay, I think that that concludes the session.